Okay, so welcome everyone to this public PhD defense by today's respondent Luca Beltramelli, who will defend his thesis with the title Random and Hybrid Medium Access for Machine-to-Machine Communication, Scalability and Energy Analysis. Luca has performed his research in the Department of Information Systems and Technology at Mid-Sweden University. I myself, Professor Mikael Gidlund, has been his main supervisor, and co-supervisors has been assistant professors Amir Mahmoud and Patrik Österberg. I will describe this process for the PhD defense a little bit, but first of all, we have 4 very important persons today, or actually 5. One is the respondent, Luca. Then I'm very honored to present the faculty opponent, which is Professor Preben E. Mogensen from Åbo University. He is also a Bell Labs Fellows at Nokia Networks. Welcome, Preben.
Thank you.
And then we have 3 distinguished members of the grading committee. We have Professor Erik Ström from Chalmers Technical University in Sweden. Welcome, Erik.
Thank you very much.
We have Professor Fortunato Santucci from University of L'Aquila in Italy. Welcome, Fortunato.
Thank you very much. Good morning, everyone.
And last we have Associate Professor Federico Tramarin from University of Modena and Reggio Emilia in Italy. Welcome.
Good morning, everyone.
So the process will be that I will leave the word to the respondent to present his work, probably around 40 minutes. After that, there will be a short technical break, 5 minutes. And after that, we will start with the discussion with the opponent. And the opponent can take as much time as he wants. And when he is ready, so to speak, it's time for the grading committee to ask their questions. And they can also take as long as they want. And when the grading committee is satisfied with their questions, we will leave the floor open to the people that are inside this lecture hall, and also for those who are logged into Zoom. And after that, we will close the session, and the grading committee will resume for discussion the outcome of this dissertation. And then we will come back and announce the decision. Before I leave the word to the respondent, Luca, I would like to ask you, would you like to defend the thesis at thesis, or would you like to add some amendments?
I have some amendment to add, and I take care of informing opponent and committee member of the changes.
And errata list. Okay, with that, I leave the word to Luca to give his presentation.
Welcome everyone. Thank you, Mikael, for the introduction. So today I will present the work I've been conducting during my research here in my PhD studies. The outline of today's presentation is as follows. I will first introduce the topic of machine-to-machine communication, focusing on the challenges and characteristics. I will then move to background, describing the proposed technologies for using machine-to-machine communication, and in particular the 2 technologies that have been considered for this study, the 2 case study considering my work. Then I will move to the more technical part of the presentation, presenting the contribution of my research in the area of machine-to-machine communication, before finally presenting conclusion and final observation. Machine-to-machine communication is a broad term that encompasses many different types of communication. However, in general, we can define machine-to-machine communication as any type of communication between devices that is autonomous from human intervention. The large-scale connectivity that is provided by machine-to-machine communication is a key prerequisite for many present and future smart application. And for example, we can think of home automation, factory automation, vehicular communication, and advanced metering infrastructure. The history of machine-to-machine communication is quite old. The first example of machine-to-machine communication can be dated all the way back to the second half of the last century in the wired telephone network and SCADA system. However, nowadays the trend is that machine-to-machine communication is moving toward the use of wireless communication, either in a licensed band or unlicensed band. So nowadays there is a lot of talk about 5G for cellular communication and how it can support machine-to-machine communication, and the competitor or the other area is low-power wide area network for the same machine-to-machine communication application. In terms of this trend also is growing because there is a growing interest towards machine-to-machine communication, and this is driven mainly by the Internet of Things vision and growing the Internet of Things market. So if we look at the requirement and characteristic of machine-to-machine communication, the list of requirement is quite long. That is because we have many different types of applications that we would like to cover. If we try to classify machine-to-machine communication very broadly, we can separate it into critical machine-to-machine that is used in applications such as vehicular communication, smart grid, and industrial control, in which the focus is on ultra-reliability and low latency. On the other hand, we can have massive machine-to-machine communication in applications such as smart cities, wide area monitoring, and logistics. For massive machine-to-machine communication, the focus is on low cost, low energy consumption, and scalability, so to support a large number of devices. The focus of my work and of this thesis is on massive machine-to-machine communication in particular. The main challenges in massive machine-to-machine communication is how the device should access the channel and how they should share the resources among themselves. This is particularly challenging for machine-to-machine communication and massive machine-to-machine communication because of the large number of devices and their sporadic transmission. In general, we can identify three alternative channel access we can use: scheduled access, hybrid access, and random access. The three offer different trade-off in terms of contention in the network and control overhead that they introduce. In general, we would like to have ideally a communication with the least possible control overhead and no to least possible contention in the network. This not only because it provides better scalability, which is important for massive machine-to-machine communication, but also helps reducing and tackling the problem of energy consumption. The objective of the thesis were two. The first was to investigate scalability and energy efficiency design aspect of novel wireless technologies for machine-to-machine in the licensed band. The second objective was follow after this first objective had been achieved, and was to build upon the knowledge and derived from the answering the first objective, and having identified the criticality and the bottleneck to the access mechanism of the proposed technologies, try to enhance this aspect towards the area of machine-to-machine communication. So again, in terms of scalability and energy efficiency. The two technologies that were identified for this study as possible case study were IEEE 2811AH and LoRa. The two were studied separately, and for each one we had I defined some research question following from the two objectives. Now I will briefly go over the candidate technologies for the area of massive machine-to-machine communication in the licensed spectrum, and try to motivate and clarify why the selection of AH and LoRa as a case study for this work. With the growing market of and the growing market value of machine-to-machine communication driven by the IoT market, we had in recent years a lot of new technologies that have been proposed in both licensed and unlicensed spectrum for massive machine-to-machine communication. So there is currently a lot of competition between emerging technologies in the area. In particular, our choice was to focus on AH and LoRa, and this choice was derived from a few factors. First of all, they have both been recently proposed specifically for massive machine-to-machine communication in the unlicensed spectrum. They present a large set of parameters that is interesting when we conduct research to investigate what is the effect of different parameters on the communication performance. They also present together, combined, they can cover a large number of use cases for massive machine-to-machine communication in the unlicensed spectrum. Lastly, and maybe the most important for this work, is that they have adopted a very different design principle when they tackle the problem of managing the access of the device to the shared channel. So a brief comparison between the two. Between IEEE 802.11 AH and LoRa, there are some commonalities, but these are limited. They both operate in the sub-1 GHz ISM band. They can support thousands of devices per aggregator point, either access point or gateway. They're optimized for small packet size. They also introduce new energy-saving mechanisms in the medium access control mechanism. However, once we look into a bit more detail, we can see some striking differences between the two. In particular, the modulation, first of all, which also is reflected in the different transmitting distance and data rate, with LoRa supporting wide area application with a smaller data rate. The most interesting point for this work was the different choice in terms of medium access, with LoRaWAN choosing to use a very simple pure LoRa. On the other hand, IEEE 802.11 AH adopted a grouping mechanism combined with the CCMA mechanism inherited from the legacy IEEE 802.11 family of standard. The different characteristic of the two technologies means also that they target different type of applications. In particular, AH target application that require a higher data rate, whereas LoRa target application that requires longer coverage distance. These are the list of the included publication in this thesis. They are divided into two groups according to the technology that was investigated in each of these paper. In particular, as I mentioned, the two technologies, IEEE 802.11 AH and LoRa, were studied separately. However, the method adopted to study each technology was similar in the sense that the first study, in both cases, represented just an investigation on the performance of the technology as described by the standard, try to identify bottlenecks and criticality that then have been addressed in the later work. I will now move to the more technical part of the thesis, presenting my contribution that have been published in this paper. The first part of the thesis covered the IEEE 802.11 AH standard, and in particular for this standard, the interest was to analyze the grouping mechanism and how that operate and how that allow the standard and the wireless technology to scale to network with a large number of devices. In literature, there were many studies conducted on the grouping mechanism. However, they always consider the case of use of DCF, so the basic CCMA-CA mechanism used by IEEE 802.11. In this case, we consider to use ADCA, which provide quality of service or a statistical quality of service. So the goal here was to analyze the performance of the grouping mechanism when ADCA mechanism was combined. The outcome, the way we approached this was by proposing use of a Markov chain, discrete time Markov chain model for the grouping ADCA mechanism. A few words about how the grouping ADCA mechanism works. It's a centralized mechanism in which the access point divide the associated station into groups, which are shown here. The station access the channel within a time window that is assigned to each group, and to access the channel, they need to contend. The contention uses, in this case, in the context of this work, uses ADCA. So ADCA is a CCMA-based access mechanism that is introduced in IEEE 802.11e, which support a statistical quality of service by means of using different contention window and interframe space. For the model presented here is summarized here. It shows that we have a combination of 3 discrete time Markov chain, one for the backoff process, one for the backoff counter freezing, and one for the queue system in each device. the model was capable of modeling both saturation and non-saturation condition in the network. To validate the model result, we used NS3 simulation. The metric considered when we look at the result were the contention delay and the normalized throughput. And here we have the scenario parameter, which what we did in general was try to change the number of group and see how that affects the performance of these different access categories or traffic categories. The first result is for the collision probability, which kind of tells us what is the level of contention in the network. So what is the probability that transmission from a device in the network will fail because of a collision. When we change the number of group, here we can see that as we increase the number of group, the collision probability decreases for both access categories. So the high priority, which in this case was voice traffic, and low priority, which in this case was the best effort traffic. We also see a diminishing return in the reduction in the collision probability as we introduce more group. The second result regarding the throughput of the system, normalized throughput. Here we can see that when we are in this condition, at low traffic generated per station, more or less the grouping is not effectively improving the throughput because it's not required to use grouping. So in this case, both access categories have the same result, and these are not affected in general by the number of groups. The situation changes when we move to medium to high traffic load. As you can see that there is a strong performance increase when we use grouping. This is the green line is the baseline for the case in which we have only one group, and the other are the case for higher number of groups. Also to highlight here that there is this phenomenon of starvation of the low priority traffic when we reach saturation in the network. This occurs when all the traffic transmission opportunity are taken by the high priority traffic. This phenomenon was well identified and was studied for ADCA, and it's interesting to see that grouping is still present when we consider a grouping ADCA mechanism. Final observation regarding this first work is that throughput can be effective at increasing the grouping can be effective at increasing the throughput in dense deployment scenario. This is true for both high priority and low priority traffic. Starvation of low priority class affecting DCA is still visible when we introduce the grouping mechanism. Finally, our observation that is more general is the fact that the grouping mechanism of AH is highly flexible. However, introduce even more parameters that must be designed to have an effective and efficient access to the channel by the station. And the design of this parameter can be challenging, in particular if we have a dynamic traffic load or dynamic traffic in the network. Which brings me to the next work, which is a hybrid medium access control mechanism for energy efficient communication in IEEE 22.11 AH. Previous work in literature have proposed the design of grouping mechanisms. However, most of them focus on the statically assignment of the parameter, which is based on some a priori knowledge. This, of course, cannot be really effective if the traffic condition in the network change. So the alternative is to use a dynamically assignment of the parameter based on real actual traffic requirement. However, given the grouping mechanism and how it operates, it's difficult to get real-time information regarding the actual traffic requirement from the device that sleep for most of the time. So to tackle this issue, the proposed approach is to introduce a hybrid mechanism for the uplink communication of the AH standard. This is how the mechanism works. We have two phases, one contention phase and one reservation phase. The contention phase is the first phase and is used by the device to transmit a small PS pool frame introduced in the AH standard that notifies the access point that they have a message or data to transmit that require transmission. With this information and with a very efficient transmission due to the small size of the packet of PS pool frame, the access point can then schedule in a TDMA manner the data transmission of the device that requires it using the grouping mechanism and hijacking the grouping mechanism of AH standard. The scheduling interval in this case is equal to 2 times the beacon interval of the access point, so it must be fixed. For evaluating the model, we use for evaluating the mechanism, we use a probabilistic model of the Beckhoff, in which model both the energy consumption of power save and non-power save station. The metric considered in this case was the contention delay and the energy consumption. In terms of scenario parameter, once again, we changed the number of the traffic load by changing the number of devices in each group and their transmission rate. Here, the comparison between the energy consumption using direct data transmission and the standard specified by the standard, and in the proposed hybrid mechanism. So we can clearly see that when the traffic load is small, the proposed hybrid mechanism is not particularly more efficient than direct transmission in the as proposed by the standard. That is because the hybrid mechanism introduce more overhead and control message exchange. However, once we move to higher traffic load, so the rightmost bar, we can see the proposed hybrid mechanism has a significantly lower energy consumption. In particular, the energy consumption can be reduced for this particular scenario by up to 55%. So the final observation regarding the work conducted on LoRa is that on AH is that the grouping is effective and reducing contention and increasing throughput in under heavy traffic load. The hybrid MEC protocol that we propose solve or avoid the issues of estimating the real-time traffic condition in the network, so to parameterize the grouping mechanism. And moreover, it can also bring to some nice energy saving due to the reduction in the contention delay. Future direction in this area is a throughput delay trade-off. So far we conducted research on the throughput and looking at the throughput and the collision probability. However, once we introduce grouping, not only we have benefit in gain in terms of throughput, but we also increase the overall delay. Another aspect that must be probably investigated further is how to avoid that congestion and the congestion problem of low priority traffic in the AH network, for example, by using some kind of congestion control scheme. And finally is to improve the flexibility of the hybrid medium access control mechanism proposed, for example, allowing multiple transmission within the same scheduling interval. Now I will move to the second part of the thesis, which regards LoRa and LoRaWAN. Before moving to discussing LoRa, I will briefly introduce LoRa characteristics and how those characteristics have influenced the research method and the research tool that I've used for this research. So we just saw AH, and we saw that AH natively have a medium access that support many type of mechanisms that avoid or help preventing a high level of congestion and collision in the network. These are the grouping mechanism, the CCMA mechanism, and other mechanisms that I have not mentioned in this presentation. LoRaWAN, on the other hand, uses a simple pure ALOA protocol, and this is not particularly good at avoid contention in the network, and so it's more reliant on the physical layer to manage the interference that will be generated by the fact that we use a pure ALOA access protocol. So in this case, LoRa does a good job, the physical layer, at handling interference by using different quasi-orthogonal spreading factor, and the fact that offers also possibility to use different channels. However, when we scale the number of devices, this may not be enough, and in particular, then the problem becomes for LoRa to analyze the effect of interference on the communication in LoRaWAN network. So a couple of words about the interference and in LoRa. In LoRaWAN, we have in general 6 spreading factors available. These are quasi-orthogonal spreading factors that can be used by the device for their transmission. These spreading factors are from 7 to 12. The spreading factor selection offers each device a trade-off between the data rate, the link distance, and the energy efficiency. According to the LoRaWAN standard specification, the spreading factors are assigned by the net server, the LoRa net server, according to the SNR of the received packet. In first approximation in our study, we always consider this then dependent on the distance from the gateway. So this is the typical scenario that we consider in studies. We have a cell with a gateway, a single gateway at the center of the cell, and the device surrounding it. And then we can see that each device will transmit using one of the available 6 spreading factors, and the choice of which spreading factor to use will depend on its distance from the gateway. In first approximation, we consider equal interval-based allocation of the spreading factor, in which the radius was divided into equal interval, and in each device we're using the same spreading factor. In terms of characterizing the effect of interference and the performance of LoRa communication, we consider two outage conditions, the classical outage condition on the SNR, the gateway, and the SIR condition, again at the gateway. For the SIR condition, there are multiple ways to approach this, because we can either assume, depending on how we assume the quasi-orthogonality of the spreading factor to behave, we can consider only the single spreading factor interference or the SIR also from other transmission using other spreading factor. In terms of values for this threshold, we reference the LoRa manufacturer of LoRa system on chips, Semtech, for the SNR value, and prior literature studies for the SAR thresholds. I will now move to describing the contribution to the LoRa. The first study involves the investigation of the performance of LoRa in a multi-cell scenario affected both by intra and intercell interference. In general, previous studies in literature have focused only on the single cell scenario. However, this is important to also study the LoRa performance when it's is in a scenario with multiple cells. This can be considered like a worst case scenario. So the goal in this case was to investigate the effect of intercell interference on the LoRa uplink traffic of a cell. We did that by using and proposing a stochastic geometry model of a multi-cell LoRa system that is able to account both for the intercell interference and the quasi-orthogonality of the spreading factor. The model is, as I mentioned, stochastic geometry model. The validation of the model was done using Monte Carlo simulation. To evaluate the performance of LoRa, we consider two metrics: the success or the connection probability and the throughput density. The scenario parameters are this one. The scenario in general had multiple LoRa cells. Must be noticed that all these cells were assumed to be identical, so they had the same radius and the same device density in each cell. These are the result in terms of success probability, so the probability that transmission from a device at a certain distance from its gateway in its cell is successfully transmitting its data. The red line represents the baseline case in which we have a single cell. So immediately we can see that when we consider multiple cells, then the success probability decreases. We also recognize a sawtooth shape of the success probability, and this is typically the case in LoRa. These spikes in the success probability are the boundary region between the spreading factor, the allocation region of the spreading factor. So whenever we see a spike, it's because we are transitioning from using one spreading factor to the use of a larger spreading factor. And larger spreading factor have are more robust and to noise. So that's why we have a spike in the success probability. However, we also noticed that once we consider intercell interference, these spikes start to also diminish in amplitude and vanish. That tells us that if we are a very dense scenario with many multiple LoRa cells, the interference can negate part of the advantages of moving from the use of one spreading factor to the higher spreading factor. Then we show the result for the potential throughput, in which we change once again the intensity of the cell or cluster in the scenario and look at the density of throughput in the scenario. Initially, we observe a linear increase of the throughput density when we increase the cluster intensity. However, around this point, we start to notice that the decrease is slow. At this point, this can be seen for spreading factor 12, 11, and 10. So that means that as we introduce more and more cells in the scenario, at this point is the point at which, when we introduce a new cell, the overall throughput in the scenario, instead of increasing because of increasing number of devices, start to decrease. And to just give you an idea of the density that we are talking about, this is a realization for the stochastic geometry model for this density. So the observation for this work where the intersilent and interspreading factor interference are a big effect on the final performance of LoRa. So if we want to get accurate result in performance characterization of LoRaWAN network in high density scenario, we need to consider intercell interference. We saw also that intercell interference affect in particular devices that use larger spreading factor. And this should be accounted whenever we consider spreading factor allocation scheme for dense LoRa scenario, in which not only we need to account for the SNR of the packet receive, but also for the interference, and in particular for the intercell interference. We now, after having analyzed the issue of interference and how bad it can affect LoRa, in particular in high density scenario, the follow-up work was to try to ameliorate the problem of interference and see how different random access mechanisms could provide better performance in the network. In this case, there were previous studies conducting or proposing the use of Doctoral LoRa or CCMA in LoRa. However, this study lacked a common framework that could compare the result and help the design of the parameter. So that was the goal that we had in this case, which was realized by using, once again, a stochastic geometry model, which allows to use within the same framework to compare the result of pure LoRa, Doctoral LoRa, and MPCCMA for the specific case of LoRa, so considering the specific characteristic of LoRa interference. The model, as I mentioned, is a stochastic geometry model for these three random access mechanisms. The validation, once again, was done using Monte Carlo simulation. In this case, we consider a single cell, having addressed the issue of multiple cell. The metrics considered were the success probability and the energy efficiency. And then once again, these are the parameters. This plot shows the success probability for the different random access mechanisms that we consider. The red line is the baseline performance, considering a pure LoRa, which is used in LoRa network for the uplink traffic. The blue line is the Doctoral LoRa, and the gray lines or black line are CCMA. We can see that CCMA has the best performance when used by the device that are closest to the gateway and uses the smallest spreading factor. However, it's affected by or hidden terminal problem, which prevent its use for larger spreading factor, which are typically located farther away from the gateway. On the other hand, we can see that Doctoral LoRa, while not performing as good as CCMA for small spreading factor, has more consistent performance throughout for all the devices in the cell. That is because it does not depend on the use of the LBT mechanism. Looking at the energy efficiency, we can see that in this case, when we change the number of devices, the energy efficiency of the three random access changes significantly. In particular, when we have a limited number of devices in a cell, and so the interference is limited, Doctoral LoRa performs the worst. That is because Doctoral LoRa has an additional energy consumption that is required to synchronize the device for the transmission and align the transmission to the time slot. This additional energy is not present when we consider pure LoRa, which then offers better energy efficiency in this range. However, once we increase the number of devices in the cell, we can see that the energy efficiency of Doctoral LoRa decreases less significantly than the rest. And this is because in this range there is a lot of interference, and so it's actually worth to use Doctoral LoRa, and the increased success probability derived from the use of Doctoral LoRa more than compensate the increased energy consumption due to the synchronization. We then try to investigate the alternative use of Doctoral LoRa and CCMA within the parameter space of LoRa. In this case, we consider the density of devices in the cell, the size of the cell, and the different spreading factor. So we can see that in general, Doctoral LoRa should be favored if we have a large cell with at the same time a large number of devices. We see a significant difference when we look at the different spreading factor region. In this case, for example, for spreading factor 7, this region is much smaller, and that is because spreading factor 7 are used by the devices that are typically close to the gateway, so they can use CCMA for more in scenario, where other spreading factors should have used Doctoral LoRa. The observation regarding this work is that there is a clear trade-off between the energy efficiency and the reliability in the use of slotted alloy, and this may not be in favor of slotted alloy if the number of devices is particularly small. CCMA can provide better reliability and energy efficiency than slotted alloy. However, this only is true if the devices are close to the gateway, so we don't have the effect of the in-terminal problem. Slotted alloy should be favored by larger spreading factor in general, whereas CCMA should be favored by smaller spreading factor. Another issue that was not really completely addressed in this work was that the synchronization affect not only the energy efficiency of the communication, but also reduce the transmission opportunity available, because if we synchronize using in-band resources, then this requires the transmission of synchronization messages. This brings me to the final work, which present and study an alternative synchronization mechanism which use out-of-band for providing synchronous communication in LoRa. For this work, we investigated the use of FMRDS. That is because it is possibly one of the best candidate technology for this application, because it offers both good indoor and outdoor coverage, and is typically offer lower energy consumption than more expensive but accurate technology such as GPS. So the goal in this case was to investigate if FMRDS could effectively be used to synchronize LoRa devices to allow for asynchronous transmission. The outcome was a synchronization / transmission scheme which was designed to be used for FMRDS, which by itself does not provide very good absolute synchronization, so we had to find some workway around it. This is how the proposed transmission scheme works. Here we can see with the red arrow the synchronization event. These are transmitted by the FMRDS using FMRDS messages and are received by the FMRDS transceiver. Between each synchronization event there is a transmission phase. This is used by the device that have been synchronized during the last two synchronization events to transmit their messages. We have in general M time slot, which are then accessed by the device. In general, we can have, when we consider the access of a slot by a station, we can have successfully or failed transmission depending on if we have one collision or there is no collision. The objective of this work was the design of the parameter of the communication and synchronization mechanism, in particular the time slot guard time, the phase guard time, the number of time slot M, and the synchronization mechanism. We've done this considering the characteristic of LoRa, not only of FM synchronization, but also of LoRa frames, and in particular looking at how different portions of the LoRa frame could be affected by collisions. Okay, so there is some problem with the slide. Sometimes they stop. Okay. For evaluating the model, we evaluated for evaluating the proposed mechanism, we evaluated the local clock and the timing error using a local clock model, which accounted for both the error in the propagation, local clock sampling, and more particular the FMRDS synchronization error, which were derived from measurements. Then we used this information to in a probabilistic model of the slot collision to design the size and of the guard interval and of the in general of the communication mechanism. To evaluate this mechanism, we use discrete event simulator. In this case, we use LoRa energy sim. The metric for this work were the success probability, the throughput, and the fairness. In this case, we study a simple scenario in which we have only one cell and one spreading factor. These are the result in terms of throughput and fairness. So in terms of throughput, we can see that the red line is the baseline throughput for LoRa, which you implement a pure LoRa access mechanism. The blue line is the synchronous communication that we propose when the synchronization is done using an ideal synchronization source or that does not require the introduction of guard time. The red line instead are the synchronous communication in LoRa when FMRDS is used for the synchronization. So we can see that with a good design of the guard interval and of the other communication parameter, performance very close to the ideal one can be achieved using FMRDS. One word about the high channel utilization that we see here, like very high compared to what is theoretical the throughput for pure LoA and Sotto LoA or synchronous LoA, is that this is derived from the low power capture threshold of LoRa. When we look at the fairness, we measure the fairness using James Fairness Index, and so that we measure that tells us what is the difference between the throughput of each of different devices in different position in the cell. In this case, we know already that by using LoRa, devices that are farther away from the gateway will have, in general, a smaller success probability. So they will be affected more by the noise. However, they will also be affected more by interference because of the power capture effect and the near-far problem. So when we look at the James Fairness Index, we can see that when we consider a pure LoA access mechanism, the fairness decreases significantly, very quickly, as we increase the number of devices. By using asynchronous communication that reduces the amount of contention in the network and the effect of interference, we can maintain a higher fairness when we increase the number of devices in the network. The final observation regarding the last work and overall the work on LoRa is that for that scenario, the effect of intercell interference on LoRaWAN performance is significantly and must be accounted for. Pure LoA is a limiting and represent a bottleneck on the performance of LoRaWAN network. And when we try to remove this bottleneck by proposing alternative access mechanisms, or such as CCMA or Sotto LoA, this comes with their own limitation that must be considered within the respect to the LoRa characteristics, or in particular of interference and energy consumption. Finally, we propose to address part of the issue of synchronization in LoRa network using band resources, the use of out-of-band synchronization via FMRDS synchronization. In this case, we look at the throughput and fairness gain, and we saw appreciable performance improvement over the use of pure LoA. Future direction in this area for LoRa are the interaction between downlink and uplink traffic, the communication delay analysis, and exploiting quasi-orthogonality of the spreading factor to have different medium access control for different spreading factor. I will now quickly go through the overall conclusion for this presentation. So, in general, the goal for this work was to investigate the random access mechanism of proposed technologies for massive machine-to-machine communication in the unlicensed band. The two technologies that were identified as possible case studies were IEEE 802.11ah and LoRa. The investigation conducted on AH showed that the grouping can effectively improve scalability of random access mechanisms. However, it requires careful design and parameterization that is not always easy to do and sometimes can lead to inefficiency. The alternative proposed is to use an hybrid channel access that can effectively be realized using the standard mechanism, grouping mechanism of the AH standard, improving the energy efficiency and scalability of the communication. For LoRa, we saw that LoRa relies heavily on the physical layer to avoid the problem of interference because of the lack of pure LoA in managing the contention in the network. So pure LoA is the main culprit for the bottleneck of LoRa scalability. When we look at the alternative random access, we need to consider always the characteristic of LoRa interference. Finally, brief outlook on the future and more general research direction for the area of massive machine-to-machine communication in the unlicensed spectrum. Well, in general, the outlook for the future is that given the predicted growth in the number of IoT devices that will be deployed in the next few years, even if only a fraction of these devices are going to be deployed and use the sub-1 GHz ISM band, there would be a lot of interference and a lot of inter-technology interference. So, whereas the focus of this work has been on scalability, but particularly on the inter-technology scalability issues, I think going forward will be more interesting to look as the number of these technologies keep growing and the number of testbed and deployment of this technology keep increasing, it would be interesting to look at the problem of inter-technologies interference, so that we do not have a phenomenon for which the success of these technologies, and LoRa in particular, may also be its downfall due to a large amount of inter-technology interference. Thank you for your attention. That was my presentation.
Thank you, Luca, for the presentation. We will take a few minutes technical break, and then we will come back with the discussion between Luca and the opponent, and then the grading committee, I'm sure, also have the questions. Thank you.